I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
space, time,
brain,
life, the universe.
Today on The Naked Scientists, I've gathered together a panel of polymaths, pundits and professors to answer the science questions that you've been emailing in. Does stress cause you to get grey hair? Why is it that when you need the loo in the car, you're fine, but as soon as you get home, you just have to go? And what's the latest in Alzheimer's research? I'm Kat Arney, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
New year, new theme tune. So let's begin by meeting the team. And we have with us Ginny Smith, who's here to answer any of your mind-boggling brain-based questions. We have Stuart Higgins. He's a physicist from Cambridge University working on the next generation of electronics. Ben Pilgrim is a fellow in chemistry at Corpus Christi College here in Cambridge. He's building nano cages to trap molecules within them. And last but not least, our very own Chris Smith, who's a basic know-it-all. He's a doctor at Addenbrooke's Hospital, but amazingly seems to know the answer to just about everything. And I do challenge you to put him through his paces. I've also got my own specialist skills. They're kind of genetics, cancer, stuff like that. So let's get started. Our first question is for you, Ginny, and it's from Lucas in South Africa.
why do we have hair under our armpits and the pubic area?
That's a very interesting question, and it's one that's perplexed people a bit. There are a few different theories. The first is that it's simply there to prevent rubbing or chafing. If you imagine you weren't wearing clothes, as we weren't when we evolved, you might find those kind of areas were quite rubby as you were walking along, so the hair could simply be to stop that. But that's not the best explanation. The best explanation that I've come across is that it's all down to mating. It's all down to finding yourself the perfect partner.
So many things in life.
So we produce two types of sweat around our bodies. We have eccrine glands, which are found all over, and they produce that watery sweat that cools us down when we get too hot. But we also have apocrine sweat glands, and they produce a stickier and slightly smellier sweat. And these glands are mainly found in your armpits and your pubic region. Now, the theory is that this apocrine sweat contains chemical messengers that can send out information to prospective mates.
These are like pheromones, aren't they? The kind of the sort of...
Yeah, so a lot of animals communicate using pheromones. We're not sure if humans do. It's still one of the big unanswered questions. What we do know is that humans are attracted to people based on smell. There have been some hilarious studies where they've got women to smell sweaty shirts.
Oh, yeah, the BOT shirt
I'm sure
studies,
we've talked about these
those,
before.
Yep.
But what they've shown is that you can choose a partner who's compatible via their smell, and it's usually looking at something called a major histocompatibility complex, which is basically how different their immune systems are to your immune system. And you want someone with quite a different immune system so that your offspring have the best chance of survival. So the theory is that our hair in those areas is to kind of wick away these smelly signals and send them out into the world so that we can find a partner.
So basically, armpit hair is there to help you get laid.
Yeah, so armpit hair should be sexy.
Well, a great thought for us all there. We've got a question for you, Stuart, not about armpit or pubic hair, but from listener Roy Learman, who says, why do embers glow red?
If you think about what's happening there, so you've got a lot of heat and you've got everything that's warm gives off thermal radiation. And this is caused by all the electrons whizzing around in the materials and the molecules of the wood. And they're giving off this thermal radiation. Now, humans do this all the time. We do this at room temperature, but we can't see it. It's in the infrared. So if you ever see one of those infrared cameras and you look at someone and they wave, you can see their hands, you can see the hot parts of them giving off this radiation.
But we don't see that. So why do we see it coming off fire embers?
So in this case, the fire is a lot warmer. It's giving off a lot more energy. In that case, the photons, the radiation that's being given off is of a higher energy, and it shifts from the infrared, the below red, into the red region of the spectra, so we can start to see it with our own eyes.
So if humans were as hot as a fire, we would glow red?
Yes, yeah, we would.
Basically, that's a thought for us all, isn't it? OK, as well as answering your questions, we have got some news stories for you. And Ben, I noticed, everyone's been talking about the periodic table. It's finally filled, is it?
Yes, it's been a very exciting week for chemistry. So IUPAC, the International Union of Pure and Applied Chemistry, announced that 4 elements number 113, 115, 117 and 118 have been discovered. Now, these haven't all been discovered in the last few days. That would be quite a coincidence. It's actually been about 10 or 15 years since scientists first started gathering evidence to suggest that these elements did exist. So there'd been gaps in the periodic table. They'd been predicted to be there for a long time. But it's all about the scientists getting enough data to be able to be sure that these elements are actually there.
The periodic table, a lot of people have heard of it, a lot of people probably recognise it. What exactly is it as a way of categorising elements? How did they know that there were these gaps in there?
So elements are placed in the periodic table depending on the number of protons, which are a particle found in the nucleus of every atom. And there's basically, the first element, hydrogen, has 1 proton, the second element, helium, has 2, and so on. And the number of protons defines what element you have. And it so happens these numbers that I said earlier, they're the number of protons that we hadn't found yet, but they should be there because it should be possible to have one with that particular number.
So how do you go about discovering a new element? I assume you don't find it down the back of the sofa.
Yeah, I mean, the problem is that there's about 90 elements on the Earth that are sort of naturally occurring. We find them around. They might be bound up with other things, but they will always be there. They're stable. An oxygen will always be an oxygen. A gold will always be a gold. The trouble with these elements is they're radioactive. They're unstable. They fall apart after a very short amount of time, sometimes fractions of a second. And so the scientists actually have to make them. And they do this by firing 2 lighter elements at each other. So, for example, they fire a calcium atom at an atom of americium. Calcium has a number of 20, americium has a number of 95, and then that adds together to make 115. Part of the difficulty is that these new ones we make, they're very unstable, they fall apart, so how do we know we've made them?
Yeah, but they sort of hang around for something in the region of about a microsecond through to a couple of seconds, don't they? I mean, someone was saying that one of these new elements, they'd only ever made 90 atoms ever.
Yeah, so one of the ones I found out, that 117, apparently 15 atoms have been observed. So yeah, you don't want to go
don't
to
spend them all at once.
You don't want to go to the toilet and miss it or something, do you? But imagine if you had a video, for example, of a game of snooker, and someone had sort of, by some computer wizardry, removed the cue ball from the sort of piece of videotape, but you might be able to think about where the cue ball was based on what the other balls were moving and how they were moving around the table. And that's a bit like what they have to do here. They have to kind of use what these heavy atoms decay into and then kind of reconstruct and then assume what they had before.
Can I just ask the really simple question, though, which is the why are we doing this?
Well, I think it's very exciting because there's something that's referred to as the island of stability. So as we get heavier and heavier, the atoms are becoming less stable. But it's been hypothesized by a number of people that once we get a little bit higher up, we might actually get back into some stable elements again, some stable atoms. And these may have new properties that we haven't been seen before. So that's very exciting.
And of course, the big question is, what are we going to call them? Because numbers aren't cool. We need brilliant names. What's the
untritium and unpentium and unseptium? Is that not sexy?
Oh no! Come on, no.
Yeah, so those names are a little dull. So they can be called after a number of things. A number are called after countries or places or after famous scientists.
There was a petition this week to call one after Lemmy.
Yes, because this would be one of the heaviest of the heavy metals.
Heavy metals, yeah.
Unfortunately, I think it has to be a scientist according to the rules. There are certainly some British scientists, Humphrey Davy, Michael Faraday, that don't have elements named after them. Even perhaps one of our most famous scientists overall, Isaac Newton, doesn't have an element. But because the research groups, 113 was discovered by a Japanese group, the others by a collaboration between Russian scientists and American scientists, I think we might maybe see a reference to Japan in one of them, one based on the name of Moscow, I've heard. And so I think that's perhaps slightly more likely.
Well, I think we shall have to see. Here on The Naked Scientists, we've been taking on your science questions. So if you're sat at home questioning, why is the sky blue? Or what's the universe made of? We're here to help. No question is too big or too small for our Q&A shows. Just email chris@thenakedscientist.com or tweet @nakedscientists. John Hockenhull got in touch with a relevant question to the party season that's just gone, so we called him up to find out what he wanted to know.
A few weeks ago covered the subject of hangovers. But why is it that some people do not get hangovers? So
well, I did a little bit of practical experimentation myself over Christmas, I must admit, and I did have one or two.
I've got a terrible one today.
And Kat is confessing that she is currently suffering.
See, I've got two sisters. Myself and one sister never ever get hangovers, and my other sister does.
I suppose in answering this question, John, one has to consider, well, what is a hangover? A hangover is a combination of dehydration, because alcohol is a diuretic and it encourages your body to lose water. And this means that the salt balance of your body goes off kilter, which contributes to you feeling not very well. The other thing that alcohol is, it's ethyl alcohol, and this is a metabolic precursor for acetaldehyde, which is about one carbon atom and a few hydrogen atoms different from the same stuff we use to embalm bodies in a mortuary. That's formaldehyde. And when you break down alcohol, one of the intermediates in the breakdown process is acetaldehyde, and that then goes around your body, fixing your tissues, and also contributes to some of the nasty symptoms. Now, why is it that some people get these symptoms and others don't? Well, there was a big study done in Australia, actually. They looked at 4,000 people on the twin registry. They found about 40 to 45% of the hangover effect is down to genes, the other half probably down to behaviour and body size and so on. In other words, what will genes be doing? Well, they'll be affecting your ability to handle the levels of acetaldehyde. They'll be affecting the levels of various enzymes in your body that break down alcohol and therefore eliminate those toxic intermediates from your body. And therefore, how your metabolism handles alcohol is going to be at least half of the situation. So if you are prone to hangovers, you're probably not going to improve through training very much. A little bit of training can improve things by increasing the levels of the enzymes your liver makes, but not very much. So it's probably better, they say, to steer clear.
So basically, I've pickled myself today.
Yeah, basically. Sorry.
It's entirely self-inflicted.
But I hope that answers your question, John, anyway.
Now, we've got a question from listener Harold, and I think I'm going to direct this at Stuart, and perhaps a topical one for the winter. He says, how do the individual arms of a snowflake know what's happening on the others so they all grow and match and remain symmetrical? I guess this is a question about how do snowflakes grow?
Well, you need a big cloud of gas and water vapour, and you need the right conditions. You need it to be nice and cold. And so at the start of a snowflake, you need a speck, you need a nucleus. And so typically this might be something like the dust in a cloud, and the water will start to solidify and crystallise around that nucleus. And it just so happens that the way it packs is in a hexagonal structure. So you have this regular hexagon that has a symmetry of 6. And so that's what gives us this kind of growing 6-pronged structure of the snowflake.
And are all snowflakes different? Is this true, or is this a myth?
It is true to a certain extent. So they have similar structure. So snowflakes will share this common 6-pronged structure due to the fact that it's the packing structure of the water underneath. But what happens after that, when these arms spread out and they start to interlink and branch like tree branches, that's more dependent on the conditions. So that could be the temperature and the exact pressure and all the different factors that might affect it. So the chance of getting those two sets of conditions to grow the same crystal, the same snowflake twice, are very rare.
Fascinating. And now it's time to hear from Dave Spence, who has a thought-provoking question. Perhaps this one could be for you, Ginny.
Well, first of all, before I can say the question, can I just say that I think you're a fantastic programme and very educational, and as a teacher would say, keep up the good work.
Oh, thank you very much.
Gold star. There you go.
Hi. My question is, if you have a species of life on a planet that perceives itself to be superior to all other life forms, thus the invention of religion, is religion itself based on intelligence, or is it based on the concept of fear of death as a consequence of that intellect?
Wow, this is a big one. Ginny, do you want to take this on? What do we think about our superiority and our that kind of thing?
It's a difficult question to answer because humans are the only species we know of that has religion. So the question is, how and or why did we evolve religion? And we don't really know, but there are two main ways that it could have happened. One is that religion evolved due to natural selection because it has a selective advantage. Those of our ancestors who became religious did better than those who didn't, and so it was selected for. Another thing is that it could be a kind of evolutionary byproduct. It may be that we evolved something that was really useful, and then religion came along for the ride as a kind of a byproduct of that thing that was useful.
I mean, I think there's an argument about that it having some sort of social cohesion, and a lot of religions have rules around hygiene and eat this, don't do that, let's do this, let's go here.
So that's one of the ideas that if it did have a selective advantage, that could have been one. It seems like religions came along around the same time that our ancestors were starting to live in bigger groups, when social cohesion would have been really important. They often involve watchful ancestors, spirits, that kind of thing. People keeping an eye on what you're doing. And if you have that ever-present person keeping an eye on you, there's this really big impetus to do the right thing. And if you're living in a big group, that's really important.
Where do you think the observation from South Africa last year comes in, Ginny, the Homo naledi findings, where these primitive people, they may be 2 million years old, appeared to be burying their dead? To all intents and purposes, these animals had a brain the size of an orange, and we know that equivalently brained animals are not known to be Einstein. So that is it that there's some sort of primitive thing that evolves that you want to have respect for the dead or whatever? David, what do you think?
I mean, religion in itself, you can look at it from two perspectives. As the lady said earlier on, as human beings started to live in bigger communities, and obviously there had to be some rules of control, let's just say. But I think also, if you look at religion, I think the concept, I mean, this is maybe controversial, but once a certain intellect starts to be perceived and the consciousness of death starts to appear, then I think that religion has a role in that play as to ease the concept of death, I suppose you could say.
Yeah, so that would kind of fit with the it's a byproduct thing, that we became more intelligent because that was useful for making tools. We gained this ability to see causes and effects, but then that meant we were looking for bigger causes and effects. We were looking for something more, and perhaps we put together things that maybe didn't go together, and we saw a divine power. And then, as you say, once you start to understand your own mortality, it's very comforting to have an idea of an afterlife. And it does seem to be something that's really pervasive all across human cultures, human religions. They all have this kind of idea of the afterlife and what to do with your dead. And I think you're probably right. It's got an element involved there.
Absolutely fantastic question. Thanks very much. Ben, let's do some chemistry now. This is from listener C. Almesto in Spain, who says, why are iridium, platinum and gold non-reactive? And presumably there are other non-reactive metals as well.
Thinking back to the periodic table again, these metals all are in the same region of the periodic table. So they're sort of the bottom right of what we would call the D metals. And if we think about why something's not reactive, well, there's sort of two reasons. One is that it's not favourable for kind of the reaction starting materials to go to products. For example, we might think of a metal reacting with oxygen and forming an oxide and tarnishing, and whether that's energetically favourable for that reaction to happen. So that might be one of the reasons. The other one is that it might be favourable for the reaction to happen, but it just happens so slowly. There's a sort of barrier for it to start. And with some of these metals, it's a bit of both, really.
So basically, the metals that don't react, it's just really difficult. You need to put too much energy in to get anything out of them.
Yeah, that's one way of thinking about it. Gold does react with some things, though. You can dissolve it in aqua regia. This was done in the Second World War.
Acid, isn't it? Basically?
Yes, it's a concentrated nitric and hydrochloric acid. It was done in the Second World War to save the gold Nobel Prizes of a couple of German physicists from the hands of the Nazis. So they were dissolved in aqua regia, hidden in a bottle of acid in a lab, and then after the war, the gold was still there. It was turned back into gold and recast, and the medals were re-given to the scientists.
Fantastic story. You're listening to The Naked Scientist with me, Kat Arney. Today, you've been drilling us with your questions. We've had some great ones in so far, including, why do we have pubic hair? Just to remind you of our expert panel joining us, we have Ginny Smith, brain-boggling expert, physicist Stuart Higgins, chemist Ben Pilgrim, and Chris Smith, medical doctor and honcho-in-chief of the Naked Scientists.
Bhavesh actually said to @NakedScientists, hello, Dr. C and crew. I'm liking that, Dr. C and crew. He says, rogue stars in the Milky Way have been observed moving around. But what is the fastest object in space? Well, I would say a photon is the fastest object in space because it's going at the speed of light. Would you concur, Stuart?
I would indeed. Oh, the photon, the speed of light, is the fundamental speed limit in the universe.
There you go. That was a quick answer, wasn't it, Kat? I bet you're
There
delighted
you
with
go.
that.
Very, very smart answer. Ginny, let's find out what's been going on in the news for you this week.
Well, I have a story that you may be able to blame the Neanderthals for your hay fever and other allergies. Ooh. Scientists have known for a while that when our ancient ancestors moved into Europe, they mated with the Neanderthals and their close relatives, the Denisovans. This means that those of us who don't have purely African heritage, we all have some Neanderthal DNA in us, and it's estimated to be around 1 to 6%. But this week, really interestingly, 2 separate papers have come out and they've shown that some of the most common Neanderthal and Denisovan genes that we have are actually involved in boosting our innate immune systems. And that's the kind of first response that our body mounts when it encounters a pathogen. So one of these studies looked at whole genome sequences and they analysed variability, basically. And they found that there were these 2 sets of genes that were involved in innate immunity that were more similar to Neanderthal genes than the rest of our genome was. And they also found evidence that these sets of genes had been positively selected for.
So there must be an advantage to having them.
Exactly. And the second paper found something very similar, looking at one particular set of these genes. So this is really strong evidence that we got these sets of genes from these ancient ancestors and that they were then selected for. So the most likely scenario was that as our ancestors left Africa, travelled across the world, they came across these other ancient humans and they were already well adapted to their environments. So when our ancestors bred with them, they kind of stole bits of their they shared their immune systems. And the ones who got these genes from the ancestors who'd been there for longer than Neanderthals, they survived better because their immune systems were more reactive to these kind of local pathogens. But it isn't all good news because these genes also seem to encourage overly sensitive immune systems. So those who carry them are more at risk of things like asthma, hay fever, because of course these are also linked to your immune system. So you might have the Neanderthal to blame when you get the sneezes.
It's something we're hearing a lot about in the media at the moment, the sort of boosting your immune system with detoxing after Christmas. And have to remember that boosting your immune system does give you allergies.
Yeah, not always good news.
Always a good one. Relevant to the change in temperature that we just seem to be having, we had a call in from Martin Fennell.
Coming to the cold season when we have to start scraping our cars of ice in the morning, and I've noticed that sometimes the ice is really easy to get off, and sometimes it seems to be chemically bonded to the windscreen. And I wondered, first of all, why that would be, but probably more importantly, can I predict it the night before so I can get an extra 5 minutes in bed?
Ooh, what do you reckon? Stuart, Ben, is this a chemistry or a physics thing?
Mixture of both, isn't
mixture of both. So I've had a couple of initial thoughts about this. One thing might be how quickly the water freezes to ice. We know that things that freeze quickly tend to form crystals that are very, very small, whereas things that I think about snow, something like that, whereas something that freezes over a long time forms much larger pieces of ice. And I imagine that sort of the larger bits of ice would be more difficult to get rid of than smaller bits. That's one of my first thoughts. And the other one might be whether the car was wet sort of before the night. So whether if there's sort of droplets that are kind of already on the car, then they might be sort of quite well adhered to the surface.
Oh, like if it's been misty or something like that.
Yeah, or just rained or something like that, sort of above freezing during the day, but then these droplets are already on the car, they freeze at night. Or whether it's just sort of moisture that comes from the atmosphere during the night. My feeling is if the car was wet already, that would probably lead to sort of ice that was a bit more stuck on.
But would the easy answer not just be to boil the kettle and pour it over? Because that would work on either, wouldn't it?
Or de-icer.
Yeah, I mean, that would work. You've got to be a bit careful with very hot water because you might lead to an expansion of your windscreen and crack your windscreen. But yeah, certainly de-icers and things like that would be good.
Stuart?
Yeah, one of the things you could do would be to the surface chemistry of the windscreen itself. If you've got a layer of a material on it that the ice doesn't want to stick too well to the glass, that might help. So, for example, a thin layer of washing up liquid, something like a surfactant that has forms basically a layer in between the glass and the water would also be another way of doing it.
It's also known as a tarp, isn't it?
Yeah,
you
exactly.
can put a tarp on it. Does that answer your question, Martin?
It does. That's great. Thanks a lot.
Excellent. Well, happy scraping. We've got a question from Calvin Armstrong who asks, how do decisions originate in the brain? Ginny, as our brainy bod, what do you reckon?
Well, as with many brain questions, the answer is we don't fully know yet. There's a very famous experiment done by a guy called Libbe, where he asked people while they were in a brain scanner to move their finger whenever they felt like it, but remember the time, and they were looking at a clock face, that they decided to move. And he found there was a 200 millisecond delay between them having the urge to move and the movement. But 550 milliseconds before the urge, he could see a pattern of brainwaves, which he called the readiness potential. So effectively, these people's brains knew that they were going to move before they consciously made the decision, which has been used for a long time to argue sort of against the idea of free will. Our brains are making these decisions and we, our kind of conscious selves, come afterwards. But more recent experiments have shown that actually this readiness potential is active whether you're deciding to do something or whether you're deciding not to do it. And there was a new study out recently where they were scanning people's brains, and when they saw this readiness potential, they then sent them a signal saying, stop yourself from moving. And actually, they were able to stop themselves for quite a long time after this readiness potential was there. So that pattern of brainwaves itself isn't enough to actually make you make the movement, but it is sort of involved.
I mean, I guess if you had to think about every single thing you're doing all the time, you'd just be freaking out. You wouldn't be able to survive.
Yeah, a lot of what we do is effectively on autopilot. It's being controlled by our brains without any conscious intervention.
It's interesting you say that, Ginny, because there is a question that's just got here from Dan Wheeler by email to chris@nakedscientist.com. And he and his fellow listener Thomas say, and this is, I guarantee, going to have everyone nodding, can you tell us why it seems that the first second takes longer to pass when you first look at a clock with the second hand? And it's absolutely true, isn't it? You must have all noticed this. And I think it comes down to what you're saying, basically, which is that the processing delay through your visual system is at least 150 to 200 milliseconds. In other words, a pretty high fraction, a fifth of a second goes by between the time that actually something is presented to you and then you actually being able to process that information through your visual areas of your brain. And it may take up to a third of a second before your consciousness then integrates that and puts that visual stimulus into your conscious experience. So when you're looking at the clock, there's going to be a delay when you first look at the clock while your visual system compares what is the clock looking like, what did it look like, oh look, it's now moved, and then it becomes a streamlined process.
The other time where you see that delay is if you've ever done that thing where you've seen something out the corner of your eye and thought that it was a spider or a snake and had that moment of panic and then noticed that actually, no, it's the garden hose or it's, some fluff on the side. You get that moment of panic because your unconscious parts, the subconscious parts of your brain register the threat, and then the conscious parts get the information from your visual system and go, oh no, hang on, it's just a garden hose, calm down. So then you can really see that difference between how fast your unconscious and conscious processing is.
Fantastic question, though. Thank you. We've got a great question in from Sandy Bennett from Australia, who says, one question in my primary science class learning about energy is, when does light wear out and how far does light travel? I'm unsure how to accurately and simply answer these questions. Can you help? I'm sure we can. Stuart, can you help?
The short answer is no, it doesn't wear out. It never wears out. It keeps travelling forever. And that's because light is actually a wave of energy. It doesn't have mass. And so things that have mass normally decay into smaller things and break down. In this case, light doesn't have it. It will just keep going forever. However, that doesn't really match our everyday experience. If I shine a torch in your eyes and it's blindingly bright, and then I stand the other side of a field and shine it towards you, it looks dimmer. It doesn't seem as bright. So what's going on there? There's different things that actually could make light wear out, as it were. And that's where the light might be absorbed by the particles of the air or the atmosphere or scattered off the dust. Or it might be actually the light just not reaching you, it's shooting at a slightly different angle.
So if there was a perfect vacuum in the field between you with the torch and me, then it would seem as bright as if I was standing right next to you.
Not quite. So if it were maybe a laser and the laser was shining and lasers traveling a straight line, that would be fine. But actually, the torch, if you think about it, the light's being made from the filament, it passes through a lens that scatters some of the light. It passes, usually got a bit of metallic foil in there as well that kind of pushes it towards the front of the torch. But even still, the light is spreading out. And so if you imagine the number of photons that are reaching your eye is actually decreasing the further away you are, because your eye is only a fixed area that can receive them.
What a fantastic answer. I hope that does answer your question, Sandy, and you can explain that to your kids at school. We've got a question here from Holly Trantham in the US who says, does cooling rubber slow its degradation? It's very hot and humid where I live, and I find that bags of rubber bands degrade faster than I can use them. I'm going to store them in the refrigerator to see if that helps. Will it? It's so irritating to find that I need some and they've lost their spring. So, Ben, will it?
Actually, the thing that usually causes rubber to go off, rather than being slightly too warm, is exposure to a chemical that degrades the rubber. So there's some types of polymer, things like ozone in the atmosphere can react with, but even without that, actually light is one of the big problems. Light can split oxygen into these radical species, these peroxides, and over time these degrade the structure of the rubber. So rather than keeping it cold, keeping it in the dark would certainly help. Now, it's interesting about the cold because actually if you cool rubber down too much, you actually cause it to decompose much faster. And this is due to the rubber falling below something which we call the glass transformation or glass transition temperature, when it sort of has these rubbery-like properties. If you go below that temperature, it becomes brittle. Now, one of the most famous consequences of this was actually the cause of the Challenger shuttle disaster back in 1986. So the O-rings, which were made of rubber in the kind of engines and the boosters for the rocket, were very cold on the launch pad that day because they had sort of very freezing, very low temperature conditions. And therefore, they weren't flexible enough to seal properly. And then this led to sort of hot gases coming out and eventually the very sad disaster. So, and this was sort of demonstrated quite famously by Richard Feynman in sort of the inquest when he sort of took one of these bits of rubber and sort of put it in a glass of ice water in front of the panel and showed how brittle it became. So I'd be careful about sort of sticking it in the freezer. That might not be the best thing to do.
But when it warms up again, wouldn't it go back to normal behaviour?
Yes, but I'd say one of the main things is keeping it out of light, and if you could keep it in a sort of airtight container so it doesn't, for example, have oxygen and so on get to it, that might help as well.
So keep them in a sealed, dark box?
Yes.
OK, well, I hope that's some good advice for you there, Holly. Let's have a bit more about what's in the news this week. So, Stuart, tell me about this. So if you're a Harry Potter fan listening to this programme, you'll probably remember the newspapers from the films where you can roll them up, and these are electronic tablets and things that you can roll up. Is this a reality? What's going on here?
So we're one step closer to this reality, and the dream. And this news story really caught my eye because this is right up my street. This is my area of research. There is the Consumer Electronics Show in Las Vegas. That's this big trade fair that happens every year. It's just finished this year, and it's basically for the tech companies to show off their latest gadgets and inventions. And the one that really caught my eye was from LG Display, and they've made this flexible screen that's about 18 inches in diameter, and you can roll up and bend. It looks like a TV screen, but on a piece of plastic that's as thin as a piece of paper.
Is this for people with sort of non-ideally shaped living rooms then? You can sort of bend it into the corner, is that the point?
Slap it on the coffee table.
Exactly.
Quite literally.
You could put it anywhere. And so one of the things they say is you can actually roll it down. Or so, you have, once you finish watching TV, you roll it up like a poster and put it in the cupboard. It has all kinds of other applications. So this technology could also be used in things like intelligent packaging, incorporating screens and circuits into packaging.
So how does this actually work? And the big question, is it actually any good?
Right, so it's a mixture of things. So we've had this technology for a while now because we've had OLED TVs. We might have these nice big flat screens. And part of the problem is that the way these TVs normally work is that you have to have a big white light behind them that shines through red, green, blue filters, the colours that make up all the colours of the rainbow that we need to see. And you basically work the screen by turning off which bit of the light is shining through which filter. So instead here they're using OLEDs, which means they have little tiny lights in there that are directly generating the red, green and blue that you need to see. And that means they can get rid of the backlight behind it, the big white light, and that makes the whole thing thinner and a lot easier to put onto a piece of plastic.
But is it actually any good? If you keep rolling it up, shove it in your pocket, get it out again, is it just going to get knackered?
Well, this is the problem because, I don't know, do you have an unbreakable ruler at school, which it claimed to be unbreakable, but I tell you, if you bend it enough times, it will break. And this is the same thing. Plastics fatigue, they have mechanical strain. And so if you look very closely at these screens, what you're looking for occasionally, especially the flexible ones, are things called dead pixels, little ones, the lights that aren't turning off or aren't turning on.
I thought I had those, but it turns out it was insects.
In your screen?
Yeah, because they put in front of the LCD, they put a fixed layer because the LCD is obviously much more delicate. But these little tiny thunderbuggy thrip things have discovered that obviously it's a nice bright light source, it's nice and warm. They can get in between the two. And I thought I had a dead pixel or two, and then I discovered it was moving across the screen. It would be there today, and the next day it's in a different place. And these insects go in there. The real bummer is they die in situ. And then you have this permanently dead pixel, but it's a dead insect. I tried shaking the screen, but it's kind of lodged in there.
I mean, given that this does sound like the stuff of the future, how close is it to being a consumer reality?
So the screens themselves are getting there. We might be, maybe 5 years away from having that into a product. But the challenge is not the screen itself. It's really the circuits and the technology around it that power the display. So how are we going to make a flexible battery? How are we going to make the processor that actually puts the display on the picture? Those are the limiting factors at the moment.
Chris Smith and Kat Arney here on The Naked Scientists, and we're putting the spotlight on you today by taking on some of the questions that you've emailed and tweeted to us. To get your questions answered in our next Q&A show, email them now to chris@thenakedscientist.com, or you can tweet @nakedscientists.
And we've got a question that's come in here from one of our listeners about yawning.
Dear Naked Scientist, this is Andrew from Urbana, Illinois. So when I was yawning, for a very brief moment, I can hear nothing of the outside world. It feels like my ears were insulated with the best earplugs. I wonder, do you share this feeling? If yes, would you enlighten me what is going on here? Thank you very much.
So what is going on? And of course, I notice Ginny's yawning. As soon as you talk about yawning, everyone starts yawning. So I apologise if you're yawning at home.
And then they won't hear the answer.
Yeah, Chris, what is going on here?
The reason is that the way that you hear stuff is that the ear canal, which is the bit you can put your finger into in your ear, ends in a structure called the eardrum. And the eardrum is a sheet of tissue which, when vibrations in air, which is what sound is, it's mechanical vibrations, those vibrations impact on the eardrum, they make it vibrate, and those vibrations are then conducted through a chain of 3 tiny bones into your inner ear, which is also known as your cochlea, and that is where sound waves effectively become brain waves, and your brain then decodes what those vibrations meant, and that's how we interpret the sound world that we live in. Now, the problem is that the middle ear, which is where those 3 tiny bones are, is connected to the back of your throat through a structure called the eustachian tube. And you need that because when the outside pressure changes, if there was no way for the pressure on the inside to be equalised with the pressure on the outside, then if you went, say, up a mountain, you'd have lots of pressure inside your head and no pressure outside, and your eardrum would bulge painfully outwards. If you go diving and you had no way to equalise, the pressure of the water would push painfully in on your eardrums. And in some people who go diving and do find that they get pressure in their ears, that's exactly what's happening. But when you yawn, you're applying a lot of pressure inside, which is conducted down your eustachian tube and pushes outward on your eardrum. And it changes the ability mechanically of the eardrum to respond to those vibrations in the air. It affects its stiffness, which means that the hearing is shifted out of the regime that most of the frequencies that we interpret as sort of speech and meaningful sounds. Your ear becomes much less capable of responding to those sounds at those frequencies when you've got that high pressure in your ear, and that's why you experience this momentary deafness while you're in the middle of the yawn.
And if people are yawning at home, hopefully that is the only time The Naked Scientist will make you yawn. We've got a question that's coming from listener Adrian Papa. So, Ginny, wrap your ears around this and tell me what you think.
My question is, how did single-celled, self-replicating organisms evolve into male and female organisms that could procreate?
Oh, the origins of sex.
Yeah, well, if we're going to talk about the origins of male and female, we do actually have to start by talking about the origins of sex. Because, of course, at first, when it was all single-celled organisms, they mainly reproduced through asexual reproduction. Bacteria, yeast, things like that still do it.
They just split in 2, don't they? It's 1 cell becomes 2, becomes 4, and off you go.
It's very, very quick. It's very, very easy. You don't have to bother finding someone else to do it with.
Buying them dinner and all that kind of stuff.
So why did we stop doing it? Well, the problem is, bad mutations can build up because you're just producing a clone of yourself. And it also means if something new comes along, a new pathogen or a new environmental influence, it's going to wipe out the whole line. So it turned out that mixing your genes with another animals' genes is a really much better way of producing offspring that are likely to survive. So sex was one of the best ways of doing this. And the first sexual encounters are likely to have been between two organisms that were effectively the same. Not male or female, both sort of somewhere in between. They just started swapping some information.
Because bacteria do this. They swap little things called plasmids, tiny little bits of DNA that they just kind of go, do you want some of that? Here you go, have that. And this is usually how antibiotic resistance spreads, doesn't it? It's carried on plasmids.
Exactly. So that's kind of the first precursor to real sex. But over time, many species then evolved to having two mating types, call them type A and type B. Now, we aren't quite sure why this happens, but it might be something to do with keeping our mitochondria in check, because only one of the two parents now passes down mitochondria. We get all our mitochondria from our mother. So it may be that A and B evolved because one of them passed down the mitochondria and the other one didn't. Now, once this had happened, it was an advantage for each of the mating types to specialise. So one type started making more smaller gametes, and that meant they could have more offspring because they could mate more easily with more of them. And the other one started putting all its resources into ensuring the health of the offspring and the survival of the offspring they produced.
All its basket in one egg.
Exactly. Yes. So that then, over lots of time, as they became more and more
specialised, give it a billion years, and here we are.
Became male and female. And of course, that leads to the whole choosy female, ardent male system that we see in most animals now. And interestingly, there's some evidence that it's a real advantage to species that do that, because it ensures that only the fittest males get to pass on their DNA, and it improves the fitness of the next generation as a whole.
And certainly as a woman, it means I get taken out for nice dinners. We've got a call in now from Derek. Hello, Derek. What's your question for us?
Oh, hello. A week or two ago on the TV, Barack Obama was being taken out with Bear Grylls doing some survival skills. And on that programme, he said how he's got lots of grey hairs these days because of the stress of his job. And obviously I've heard that lots of times, and I think it's a myth. I think my wife disagrees with me. So I think it's just age. So I wondered what the naked scientists thought.
What a fantastic question. Yeah, I mean, I've been super stressed lately and I've got more grey hairs, but is that just because I'm getting older?
Have you got any grey hairs?
Yeah, I know, but you can't tell because I dye it all.
Really?
Yeah.
I thought that was natural. I was just thinking to myself, nice blonde hair like that, fancy dyeing the roots black. I was wondering what that was all about.
I like the badger look. But what is this, Chris? Does stress actually cause grey hair?
Well, people have looked at this in some detail, actually. And there's not really a consistent story here. There's a clear reason why hair goes grey or white, because the natural colour of hair, it's a protein called keratin. It's the same protein that makes your fingernails and toenails, and the natural colour of that protein is white. And the reason hair is coloured is because when hair grows out of the hair follicle, which is a little ring of stem cells embedded in your skin that makes the hair, there is another population of cells in the follicle called melanocytes. And melanocytes, as you probably know, the clue is in the name, make melanin. And there are different flavours of melanin, the chemical. There's what we call eumelanin, which is a very black colour, and there's pheomelanin, which is a more yellow colour. And the different ratios of these, the black to the yellow, affects the colour of the hair. And these melanin pigments are added to the hair as it forms, and that gives it its colour. For some reason, as we age, the hair follicle soldiers on, but the melanocytes peg out and die. They stop making a colour contribution to the hair, and it reverts to its natural state, which is a white colour. Whether or not this can be the consequence of stress, actually, we just don't know. One way that could happen is because, for instance, they become biochemically stressed. Perhaps when you're under periods of extreme stress, it could biochemically stress the hair follicles. Not really any good evidence for that. Another reason is people have speculated, and it's certainly been shown in animals, that there's a build-up of hydrogen peroxide at higher levels in hair follicles, and that hydrogen peroxide can damage the melanocytes. So perhaps, for some reason, when you're stressed, you have less ability to defend yourself against hydrogen peroxide attack. But on the whole, we're pretty unconvinced, and it's probably genetic, because some people keep their hair colour for much longer than others, and that tends to run in families. So actually, it doesn't look like Barack Obama's grey hairs are down to increased stress in the job. It's probably just a lack of Grecian 2000.
Well, and it's been 8 years since he was elected. Let's have another quick question. This is from Grant Burton. Ben, why does water go off?
It's almost always because there's something in it. I mean, water is an inherently stable molecule. In fact, they've found water that's 2.6 billion years old, sort of buried deep underground in Canada, and nothing's happened to that. The problem is that if there are small contaminants within the water molecule, sort of microbes, things like that, then over time, if they have the right conditions, these microbes can sort of grow and proliferate and make toxins and so on.
So it's not the water, it's the stuff in it. Well, here's one that we can have a go at. Stuart, what do you think of this one? It's from listener Enzamal Hack from India, who says, because plastic is so polluting, could we just send all the plastic in a rocket to the sun?
Wow, what a question.
That's a solution right
presumably.
there.
You don't mean the Sun publications?
No, not the sun. The sun at the centre of our solar system. Can't we just fire stuff? I mean, generally, can we just fire stuff we don't want into the sun?
Well, we can. We occasionally, old spacecraft and things, maybe not towards the sun, but are bashed into planets all the time to get rid of them. But in terms of plastic, the problem is the sheer quantity of plastic that we have. So last year, the Earth used about or produced about 300 million tonnes of plastic. 1 million tonnes is about the weight of 750 Empire State Buildings. It's a massive quantity.
Okay, so in terms of like the jet fuel that we'd need to get a rocket made of that much plastic up there, it's not economic, is it?
It's not. So I did a quick back of the envelope calculation, as a stress.
It wasn't a plastic envelope.
It wasn't a plastic envelope. We can't
write them, can you?
Plastic
window in it, though.
Yeah. So the heaviest lifting rocket we've ever had was Saturn V. It was the rocket that took astronauts to the moon, and that had the capability of lifting 50 tonnes-ish to the moon. So if we think, actually, it would take 6 million rocket launches to get all the plastic from just 1 year up towards the moon, not even to the sun. And if we think there are only about 85 rocket launches a year, that's about 70,000 years it would take just to shift last year's plastic.
And Enzamal does go on to say that, you know, this use of plastics is clearly bad and we should stop using them. But are all plastics bad? Maybe Ben as well, you'd like to come in on this. Are all plastics bad, and are there any really viable alternatives to get us off our fossil fuel plastics?
So plastics are a material called a polymer, sort of formed from long chains. And part of the problem is that these chains are quite chemically unreactive. They persist in the environment because sort of the microorganisms can't sort of attack them and start to break them down. But there has been a lot of work recently on more biodegradable polymers. So these are ones that still have the sort of necessary mechanical properties to be a useful plastic, but that can be sort of attacked on over time by the microbes and, you know, might rot away in the ground after a year or two. And certainly they wouldn't be as bad because eventually they would kind of go from a landfill site, unlike the ones at the moment.
Stuart, what do you think?
Well, I think this is it. So one of the things in our field, we were talking about plastic electronics earlier, and one of the challenges we have to consider as we make things is what we're going to do with all the plastic we're using and generating. So I think further research into biodegradable plastics and how we process them, if we can do recycling on them, is really important.
Yeah, I guess what you're saying about the flexible screens, you know, if you kind of throw it up, put it in your pocket and eventually it dies, you just chuck it away. Is there any progress in trying to recycle these kinds of electronics?
Yeah, so in general, you can recycle some electronics. You can try and recover the metals and things out of them. But this is very energy intensive. It takes a lot of energy to do. And so there's always a trade-off there. So maybe if we look at ways of developing new techniques and new materials, new biodegradable polymers, that would be a better approach.
Excellent stuff. A question for you, Jenny, from Paul from New Zealand, who wants to know, what progress is there in Alzheimer's treatment? Let's go for a biology question here.
Well, it's quite a difficult question because actually we still don't fully understand what causes Alzheimer's. Now, Alzheimer's is the most common form of dementia, but it is only one form of dementia. There are other types. These are brain diseases which cause problems with thinking, memory, and often all sorts of other areas, including language. One of the long-running theories is that what's causing Alzheimer's is a build-up of a protein in the brain called beta amyloid. And you can actually see sort of lumps of this in the brain of people with Alzheimer's.
They're kind of little tangles and plaques and things like this, aren't they?
Exactly, yeah. And so a lot of the research has been looking into whether you can break those down. The theory being if they're what causes it, then breaking it down should improve people. And some mouse studies have shown improvements when they've broken down these plaques and tangles. But interestingly, research that's been coming out recently has shown that in humans, breaking these things down doesn't always improve people's symptoms. And you can also get some people who don't have any symptoms, but when you look at their brains, they do have these build-ups of these proteins in them. So now people are starting to think, well, actually, maybe it's not a direct cause and effect thing with these proteins, and perhaps we should be looking in kind of other directions for potential treatments. So at the moment, there are a few drugs which can help with the symptoms, but we don't have anything that actually stops the progress of the disease. But there's a huge amount of work being poured into trying.
Because I know from the genetics perspective, lots of people are hunting for the genes involved in Alzheimer's. The problem being, there's lots of different types of dementia. And even if you can find a gene or a gene variation that increases the risk, we don't know if there's anything we can do about it to mitigate it. That's I guess, is the biggest problem, isn't it?
There is a little bit of research that's coming out that's quite interesting about what you can do throughout your life to keep your brain healthy and hopefully stave off Alzheimer's. And that's things like keeping active, lots of exercise, keeping social interactions going, keeping your brain active.
Doing things like, Sudoku and puzzles, and I guess listening to the Naked Scientists
yes,
keep your brain
definitely.
active.
And also social interaction. So seeing people and talking to people seems to be protective. And what you eat's also important as well. So lots of green veg, berries, nuts, olive oil, all of these things have been shown to help keep your brain healthy.
All the good stuff. And now we have a fantastic question to round us off from a listener who just needs to know the answer.
Hi, I'm Peter Robinson from Port Douglas, Australia. Can you tell me why, when you're in a car and you need to go to the toilet, you can hold on for a really long time, but when you get home and you know where the toilet is, you can no longer hold on? Thanks.
Oh, wow. Just the nods around the table. Everyone's like this. It's like, no, I don't need the loo. It's, oh, crumbs, I'm nearly home. Quick, let me at it. What's going on there?
I think this is a case of mind over matter, or maybe more accurately, mind over bladder in this case. When you are stressed about something, and I would put it to you that being stuck in a car on a motorway with an overactive bladder, thinking, crikey, where is the toilet? This is a stressful situation. And this will initiate your fight or flight reaction, which is a part of your autonomic nervous system, which is out of your control. It's under subconscious control. And when you are under stress, then what happens is that you send very powerful supplies of nerve impulses to your guts to turn off your intestines and to your bladder to make your bladder relax, because the last thing you want to do when you're trying to fight or run away is think, I need a wee. And this deters the bladder from activity. Now, when you get home, though, you now know, respite is within my grasp. I am nearly home. And what then happens is that those nerve impulses that were strongly inhibiting the contraction of your bladder and were making your bladder relax and relax and relax, those nerve impulses are now turned off. And so now the bladder begins to gain activity and begins to compress the urine, and you become much more exquisitely sensitized to the stretch in your bladder, thinking, I really, really, really need to go to the loo. And so I'm going to run to the loo. And that's the reason why. I think it's because it's a psychological thing you now know that helps at hand. You know you can make it. You now feel much more relieved before you relieve yourself. And so you begin to then think, now, I really do need to go to the loo.
But of course, you should have gone before you left. That's always the thing, isn't it?
I think there's a Pavlovian element as well, in that you associate seeing a toilet with going to the toilet. So seeing the toilet makes you need it more. I know that for me, if someone mentions the word toilet, it makes me want to go.
Like turning the taps on and things like that.
All of that. And terrible.
Just ruin everyone this evening. Anyway, that is all we have time for. Huge thank you to our wonderful panel this week. We've had Chris Smith, Stuart Higgins, Ginny Smith and Ben Pilgrim. Many thanks to Greer Jackson and also to Felicity Bedford for producing this week's show. Join us next week when we're snuggling up and going into hibernation to see what we can learn from the animal kingdom. The Naked Scientists comes to you from Cambridge University and is supported by the EPSRC, the STFC and Rolls-Royce. Until next week, goodbye from me and the rest of the team here.